Okay. Hi, everyone. I'm Abbas, and today I will be talking about the motion planning and control section. So motion planning is the task of generating a safe, comfortable, and law-abiding trajectory for a self-driving vehicle. Now, before going into details of topics in motion planning, let's just recap first why we need end-to-end motion planning. So the traditional approach in motion planning is just assuming perception and prediction is a separate task, motion planning a separate task, and also controls a separate task. And for each of them, a lot of engineers work on improving the efficiency independently, and the entire pipeline is not optimized together. So, and we have these very low small channels between one module to the other. So moving towards AI first approaches, one can just replace the entire pipeline with just a large neural network or a model, deep model, and directly go from map and sensor data into the action, whether it's just control or trajectory. But this approach is very difficult to interpret. So if anything happens, like an accident or something like that, it's very hard to trace it back to where in the system the error was. And it's very hard to show that the system is safe. Instead, our approach is moving towards interpretable end-to-end motion planners, where we still keep the modular parts of perception, prediction, and planning and control, but widen the channels between what information is passed from one module to the other, and keep the entire pipeline differentiable so that we can optimize the entire pipeline together. So what this does is that the upstream tasks are being optimized such that they're good for downstream tasks, because that's the end goal, to basically be able to produce a maneuver or drive the vehicle in a safe and comfortable and law-abiding manner. Okay. These are the topics that I want to briefly touch upon about motion planning. So what kind of inputs we usually pass to these models, like how the models are created, what kind of architectures, the kind of outputs, and also briefly talk about learning, interpretability, and interactions between ego and other actors. So let's first talk about inputs. So one of the very straightforward inputs to motion planning models could be just RGB images from cameras. Now, this is a natural kind of sensor data. It's what probably humans use to drive, and it has very rich data. Instead of just passing an RGB image, you can also perform some semantic segmentation on them, and then pass this to the motion planning model. And hopefully, with providing this more semantic information, the planner can understand and learn better decision making. So the strength of this sensor is this kind of data is that, first of all, the sensor is very cheap, and and the data kind of format is very suitable for example, a CNN model. But then it's very much affected by the lighting in the environment, and it lacks accurate 3D information. So it's a bit hard to understand spatial information, for example. An alternative, or something that complements that camera sensor, is LiDAR, and using LiDAR point clouds. So, for example, in NeuroMotion Planner, the LiDAR is kind of converted to a bird's eye view kind of image, and then processed for generating cost maps or motion plans. Now, this sensor is robust, gives you robust measurement. It's not too much affected by the lighting condition, and it has accurate 3D information, which will be very useful for planning. But it also lacks semantic information. You don't know what was the surface that was hit by the LiDAR ray, and also it's a very expensive sensor. So one thing that comes free with the LiDAR sensor is this concept of free space. So you can easily build that by just assuming any cells or voxel that the ray passed is kind of free until it hits a surface. So this provides a very good auxiliary information to motion planner to know where the free spaces are and where the actual surface in the environment is, and is already available in the LiDAR. But it's very there are not too many good backbone architectures that can make use of such data. And also similar to LiDAR, bird's eye view, it has the same drawbacks. Another type of input is bounding boxes, whether it's perception or prediction into the future, that are usually, for example, rasterized and passed to a motion planning model. And usually the channels are kind of used to represent different timestamps for these perception or predictions. Or the actual trajectories can be used in sense of like affordances, like distance of a ego vehicle or a trajectory to these future predictions of obstacles. Now, these are this is a lightweight representation, but it doesn't fully expose the challenge of processing the sensor data. For example, what happens if the detection flickers a little bit? What's the effect of that on the downstream? HD maps are one of the most useful inputs to planning, because maps provide a really strong prior on where the ego can move, how it can, what are the different roads, different lanes, and it's basically a very good rich prior for motion planning. Now, the most easiest way to use these maps are just rasterizing different layers of map in different channels. For example, where the center lines are, or where the boundaries are, or red traffic lights, or sidewalks and things like that. Now, this is a very simple pipeline again, and you can use just CNNs to process this, but it's very hard to encode prior knowledge about what they mean for the motion planning task. Alternatively, we can use affordances for representing this map information. For example, we can say for a key plane or lane following action, we can just measure the distance to the center line, or distance to a stop sign or a yield sign. And in this way, we can easily encode the prior knowledge. And also, but it's very hard to come up with these affordances, and because they're kind of very domain knowledge, and it's basically handcrafted. So the other information is the intention. So basically, as the planner has to plan a trajectory that moves towards a given route, because after all, we are trying to kind of get to a destination. Now, these routes can be represented by sequence of lanes, and it can be, for example, rasterized like here, or we could just extract high-level actions from the route. And we don't really have to have a route planner. We can use, for example, off-the-shelf navigation systems, and they already provide us with actions like turn left at the next intersection or things like that. Now, one way to process these high-level actions is to train a separate header for each of these actions, and add inference based on what the actual high-level action is, we can just pick the right header. Now let's briefly go over like the models. So there's no like standard or there's no standard like architecture for in planning, but usually CNN networks are used to process sensor data or images. LiDAR, RNNs are used to encode or decode temporal actions or temporal information, and MLPs are used to process or encode discrete actions or very low dimensional data. And recently, transformers have been used because of their like self-attention mechanism that can attend to different parts of the input that are more useful for the decision-making part. Now let's look at some of the outputs. So the most straightforward output is just outputting steering or acceleration, because that's basically the final goal at the control level. This is very straightforward, very simple. One level further is just to output a sequence of waypoints or a complete trajectory. Now, this trajectory can still be converted to like a sequence of controls by just having a control in between, which can be just a simple PID. Now, this is a simple output representation, and it's well studied in imitation literature. But it's hard to encode prior knowledge and lacks interpretability. Now, let's see what other outputs we can have in the planner. So the next one could be just outputting a cost or a cost map. And this is very well aligned with traditional planning approaches where you have an objective function and you want to find a trajectory that minimizes that objective function. So, for example, in Neural Motion Planner, a spatial temporal volume is generated where each pixel or voxel in this volume has a value that represents the cost of ego being at that place at that time. Now, with this output representation, it's easy to encode prior knowledge, and it's well aligned, again, with the traditional planning approaches. But the difficult thing is that there's no direct supervision on this cost volume. And it's very, thus it's very hard to train. Another type of output is affordances. So we can predict some features like distance to the center line or distance to other objects. So very lightweight output. And also it's been shown that if we can have like a multitask formulation where other than planning, we are also outputting some other auxiliary information like object detection or segmentation. This can help the planning task a lot. Okay, so let's quickly go over some of the learning methods. So the first learning method is just open loop learning, where while we are learning the planning task, the predicted plans are not really executed. So, the most common open loop learning approach is behavior cloning, where the model observes the expert states and tries to imitate expert actions. Now, the loss function can be a simple L2 on the expert controls if the output is controls, or we can use structured prediction loss, for example, max margin if the model is outputting like cost function and then followed by a minimization step. We can also, while doing this imitation learning, we can also try to learn a word model that has been proven to be helping with the imitation task. Now, these pipelines are very straightforward. As we can see, we can just load the data, the input data and the labels, and the pipeline is super simple. But and also it has a high sample efficiency, so all the examples are very interesting and very fruitful. However, the issue is that because the planner is at the time of training is trained with optimal states, basically states that are a result of optimal, like an expert action. The distribution that it sees at the training is different at inference, because at inference is basically the policy itself that is kind of generating and visiting different states. Now, there are ways to mitigate this issue, for example, data augmentation, but still the fundamental problem exists. Now, moving on, we can move to closed loop training, where as the learner is kind of learning the planning task, it's also executing them in a like simulation or real world and seeing the result of those chosen actions. So with this, there's no difference between what the learner sees at the training step versus the inference step. Now, the prerequisite of this is that either we have to kind of learn this model in real world or in a realistic simulator. Now, the question is for these states that the learner visits while it's executing the action, what will be the supervision? So the first approach we will talk about is the imitation learning approach that makes use of an interactive expert. So we assume that there is an interactive expert that we can just query what the optimal action in a state is. And so dataset aggregation, or Dagger, propose an approach where an interactive queryable expert is used to label new states, the learner policy visits. The policy is then retrained on the new data, and the whole process repeats iteratively. But it's very hard to find a queryable expert, right? That's why there are works that has been proposed to tackle this, which is for example, policy distillation, where we train a model that has access to some privileged information, for example, ground truth position of the objects, or ground truth future trajectories of the actors in the environment. And then, so when we can train such a model using, for example, a simulation, and then try to build a policy that uses the sensor, but tries to imitate such a privileged agent. Now, the issue with this is that it's still the learner will be the performance of the learner will be upper bounded by this suboptimal expert. Now, we can also encode explicit learning signal through reward design. So some works, and this can be done again in real world, but it's very unsafe and not scalable. We can also use simulation to kind of perform such learning task, but the prerequisite is that we need need a realistic simulation, and also the sample efficiency can be prohibitively low in simulation. So, what are the approaches to improve sample efficiency? One way is to use approximate world models. For example, we can assume that the actors in the environment are on rails, just following the ground truth trajectory, and they're not reacting to the ego action. Another way is to, instead of planning in the continuous control space and a single action, we can basically the policy can generate plans in trajectory space. And basically with this, it can consider a more long-term future, and this can help with the reasoning of in this task. It's also very important to have targeted scenarios. So usually like free flow traffic or nominal traffic is used to train these emotion planning closed loop. But it's been shown that if we have targeted scenarios that are very safety critical, for example, aggressive cut-ins or like a lead vehicle just suddenly braking hard, this can really affect how quickly we can train a planner that is safe and also can show good performance on a diverse set of scenarios. Also, we can incorporate some real world data. For example, we can train through imitation a model first and initialize the model with those data. And then hopefully with that, the initial exploration in RL can be more useful. And then, or we can just have the imitation loss plus a very sparse reward for the actions that the ego has chosen, without needing to come up with a very tedious reward function. Cool. So we have talked about learning. Now, the next topic is interpretability, which is very important to understand. Like whenever a motion planner makes a decision, we want to understand like why it made that decision, and we can trace it back to like where the error, for example, is coming from, if it happens. Now, in this section, we go over a few works, starting with the neural motion planner, and then moving on to DSCNet. Now, these two first planners are based on object detection. And then we talk about instance-free prediction used in planning. And also talk about approaches that combine these two, like unstructured cost and like structured cost based on predictions. And at the end, we talk about works that try to also predict a map of the environment and hence do not rely on HD map. So end-to-end neural motion planner starts by processing the LiDAR and map and generating a fused feature map. And then from there, it generates a cost volume that is a spatial temporal volume where each voxel has a number that shows like how costly it is for the ego to be in that place. And along with that, it generates detections and trajectory predictions. Now, in order to do planning, what it does is that it samples a number of candidate trajectories that represent different maneuvers. And by indexing the cost volume along this trajectory, it can grab the cost of each waypoint, and then the sum of the cost over the trajectory horizon will be how good that trajectory is. So basically, it does the cost minimization, and the best trajectory is chosen for execution. Now, here's a video that shows how it performs. So these are the detections and also the predictions. And at each time step, we are showing just the low cost region. And then the final trajectory is the red one. So we can see it first in case of lane follow, it's kind of predicting lane follow well. And it also has some lane change kind of suggestions there, low cost region. Here, for example, it knows that it can either go continue moving on or like turn to the other side. And here it kind of it's showing like nudging around a static obstacle. So there's still some issues with this approach, and one obvious one is that the cost volume is not conditioned on the perception and prediction. And The second one is that the predictions are single modal, and they're just one possible future, but in reality, the future can be like multimodal. We don't know what's going to happen. So in order to tackle these issues, the STNet proposes a model that, first of all, it shares computation similar to other models. It predicts socially consistent multimodal predictions. Also, it can use prior knowledge to in the planning, such as, okay, like ego should not collide with other actors. So the way it does is that it basically similar to NMP, it detects objects. And in order to do prediction, for each actor, it samples a number of trajectories. And then through message passing between each actor, modeling the interaction between actors using pairwise energies, it can come up with distribution of over those trajectories that are consistent between actors. And then the planning can be done just by using these distributions and prior knowledge that, as I mentioned, to cost each sample trajectories for the ego and then pick the minimum cost. So here, for example, we can see like these are the distribution of each actor being like where it will be in the future, and each color it represents different time steps. And as we can see, for this actor, it is able to predict multimodal future. And some video that shows how the planning works here. So the plans here are just obtained using minimizing the collision cost and some other costs based on the map and etc. Okay, so up to now, what we talked about the objects in the environment are first detected, and based on the detections, there are some prediction generated, and then planning works by taking account those predictions into account. So, but what if for example, the detection scores flicker a little bit, and then all of a sudden we don't see a very important actor? So that can cause a very dangerous accident. So P3 proposes to, instead of using these instance-based detection and prediction, to move on to a semantic occupancy prediction and using those in the planning. So the network basically generates scene level occupancy representations, and then the planner uses those occupancy predictions plus some other subcosts that are coming from map and comfort, and generates a trajectory that is safe and obeys traffic rule and is comfortable. So it's very easy to kind of still encode prior knowledge in such a planning. Now let's look at the occupancy representation. So it's not just that we want to know that the space is occupied sometime in future. We can also have subcategories in terms of different classes of objects, like semantically what they're doing. For example, it's a parked car, or it's a oncoming actor, or on a conflicting lane. So these can potentially help the planner to kind of know the semantic of each occupancy and plan accordingly. So the architecture here, I think Sergio already went over this, but basically at the core of it is just having this recurrent occupancy update that, given an initial perception in form of occupancy, it can also predict future occupancies. And the planner, as I mentioned, minimizes the cost. The cost consists of the occupancy, for example, the driving at the center, and a number of other costs that are related to routing and following traffic routes. So here are some example videos of how the planner is doing. So the solid box is representing the plan trajectory, and the other one is kind of the ground truth. As we can see, we are kind of able to predict different semantic of occupancies. And as the time goes by, it gets more uncertain and uncertain, which makes the planner kind of a bit conservative towards future. Now we have seen how NMP generated like unstructured cost. It's very hard to kind of supervise that. We also have seen P3 generating cost volume in terms of occupancy, which we know what it is. It's interpretable. Now, is there a way to combine such these two paradigms? So basically, the unstructured cost can kind of capture some neglected or things that are very hard to explicitly represent in terms of driving. And the structured cost can be just things we know about and some prior knowledge. So this work, STP3, basically follows such approach. And they both used like some protocol, some rule-based cost, plus some learned cost, and aggregate them to do such a planning, which is shown to be useful. Now, up to now, what we talked about, all of the approaches as input receive an HD map. So as I mentioned, it's a great prior. But in order to use the map, we have to be able to accurately localize within that map. Now, Andre will talk about like some localization methods later today, but what if the localization fails or is a bit noisy? So as you can see, it can be catastrophic because the ego then thinks that it's somewhere that is not, and may act like in a very abrupt way and aggressive motion to correct itself. Now, also, like one of the other drawbacks is that like it's very unscalable to kind of assume that we have map everywhere. So on the other hand, mapless driving is fully scalable, and but the issue is that up to now, most of the autonomy stacks are kind of based on this assumption of having a HD map, and hence, like, we need to kind of overcome this issue. So MP3 tries to tackle this mapless driving. So, like, other than occupancy prediction and flow prediction, it also predicts online map, which consists of different layers, different semantics, as I go through later. And then, given these representations, these are passed to the planner, and then planner tries to use this book. But the issue is that planner also is based on like a lot of map representations, for example, for the routing or for generating common sense maneuvers like keep laning or following a turn or lane changing. So we need to find a way to also like solve that issue. Okay, so first let's talk about some of the semantic layers that MP3 generates. For example, drivable area, where we can drive, intersection, or some reachable lanes from the current position. And also, obviously, we need to also know the occupancy of other objects as well as their motion in future. So in terms of routing, again, we can rely on an off-the-shelf navigation system that generates commands like turn right in 50 meters, right? So the way we tackle this is by training different headers based on these discrete actions. And then the output of this will be a layer, an occupancy, not an occupancy, but a special layer that shows where the route is. So basically, the output will be just a 2D image where the pixel is kind of high value if it's part of the route. The other challenge was to generate actions for the ego, which are basically the trajectories. So in traditional planners where the map is given, we can, for example, use lane relative trajectory sampling to kind of sample trajectories that are following that lane with some variations. But here, the only thing we have is the current state of the ego, and we don't know where we are on the map. So the approach can be just retrieving a set of trajectories based on some previous experience, and then using those. But this should be really conditioned on the current state of the ego. For example, as you can see, based on the current steering and velocity, different sample sets are retrieved. And then, as usual, we have a number of cost functions that are used to evaluate each trajectory. And other than safety costs like occupancy or headway, we also use the map layers to cost trajectories that are, for example, going out of the drivable area or going out of like reachable lanes, or are not basically following the route. Now, the relative importance of these subcosts are also learned with the end-to-end with the model. So here is a video of this model in action. So on the right, you're seeing the occupancy predictions, and on the left, it's map layer prediction. So this is running in closed loop. The black rectangle shows the ground truth, and the other one is basically the closed loop kind of execution of the plan. So as you can see, it's very conservative. You can distinguish the route given that command, turn left command. And my favorite one, I think is next one. Yeah, here you can see that it detects an occluded pedestrian. And because of that, the planner slows down a bit compared to the ego, to the ground truth. Okay, so there are also some other proposed approaches towards mapless driving. So one of them is being presented in this CVPR based on transformers. And this work performs mapping, object tracking, and future occupancy. So it basically mixes the instance-based and instance-free approach. And then the plan is optimized with respect to the occupancy. Even though it has instances concept in the model, it still receives a scene level feature map when it's predicting the occupancy. So hopefully that can avoid issues that are kind of that we mentioned about like flickering detections and things like that. And we still can kind of not miss like an object in the scene. Okay, so let's briefly talk about reactivity. So as we can see, like planning with just considering the marginal distribution of what happens in the future is very difficult, and it's unsafe because it mixes different future possibilities. So now on one end of the spectrum, for example, in this example, the rightmost vehicle will yield to the ego car and make the left turn after the ego passes. And in this case, that vehicle reacted to our ego intended plan, and the SDV can just continue without hesitation. Therefore, the first difficulty in planning in an uncertain world is that we need to consider the reaction of other actors to the ego plan. Otherwise, we will be very conservative, like overly conservative. And then while we are doing this, the other difficulty is that there are very unlikely events that could happen. For example, here in this example, the other actors, for example, the one that is making that unprotected left turn, can just cut off ego and try to pass through the intersection. So we should also be very careful about very low probability events. Now, to consider the reactiveness of each actor, a naive solution is just to simply sample a set of potential ego trajectories for each. And for each trajectory, we can make conditional prediction and evaluate the scene based on those conditional predictions. But this is reasonable, but it's very computationally expensive. Now, what are different ways to make this more efficient? So there are implicit ways, such as this pipe kind of pipeline, where the interaction between different actors and ego is kind of computed implicitly through just tensor fusion. We can also use explicit approaches like deep structured model, where the interaction between ego and other actors are represented by just pairwise energies. But then in this explicit approach, the assumption is too strong, and it may not generalize well to dangerous situations. The other problem that we mentioned is handling low probability events. And so as we can see here, just assuming, just planning a single trajectory, and then which will be dominated based on the most probable prediction, it will just ignore the fact that there's a low probability event that car could just come into the intersection. And hence, when we execute such a trajectory, we might end up being in a state that is very hard to handle. So alternatively, in this situation, we could just slow down a little bit, and then we could basically be ready to react to both of the scenarios. So what we can do in these scenarios, based on the lookout work, we know that we can replan every time that there's new information, and based on that, what we can do is to choose just a single short-term action. It could be just like a 1 second trajectory, and then postpone the decision about different future possibilities by just assuming that we can replan after that and react to those possible futures. So how is this? This is done in the lookout work. It's basically just sampling different trajectories that represents different short-term actions, and then sampling conditioned on the end state of the ego at the end of those short-term actions, and then the optimization will look something like this, where the cost of the action is considered as being just being able to react to any of the possible futures. So we should be very conservative about short-term action, and but the long-term action, as long as we have a possible response to different futures, we can just be okay. So. And in this work, again, this cost function C consists of collision costs and safety, comfort, and things like that. So an example of what will happen with such an optimization. So here we can see, if we just continue with the current speed, in this feature with which colored blue, it should be okay, right? We have a smooth ride and pass the intersection. However, if we consider the other possible future that was generated by the scene prediction, we need a hard brake to avoid that low probability event, right? So overall, this action is not very safe, or it's not, at least it's a bit costly. But if we slow down a little bit, we we will still be okay just to for reacting to this blue scenario. And also we will be okay responding to that low probability event, right? So that will be basically the preferred action, short-term action that we can use. So which results in a very smooth driving. Now here is a video showing Lookout in action. So we can see here, for example, how like different trajectories are generated to respond to each of these like cuttings from that vehicle on the left, and hence we don't quickly brake there, but smoothly pass through that intersection. Okay, so in summary, for motion planning, we talked about different input modality architectures, different output representations, as well as interpretability and reactiveness. Now, let's quickly go over controls. So the job of the control module is to track a planned trajectory, and that's needed because we know that the controller is not perfect. We cannot really know what command we should issue to basically follow the trajectory. And even we do when that command is executed, due to environmental errors and things like that, the car can just have some offsets toward between the actual position and the intended position on the trajectory. And so one thing is that there are also constraints in the system. Either the actuation has constraint, or the product in terms of like how much we can diverge from the planned trajectory, as well as like the ride comfort. And the metric that we use obviously is just the tracking errors in speed and longitudinal lateral errors. So one common approach towards this is optimal control, where you try to find a sequence of controls that optimizes an objective function, and this objective function is kind of includes the tracking errors in terms of speed, longitudinal, lateral errors. And the constraints can be just be present in the optimization, and the horizon enables us to be a little prepared for the future. For example, if the plan is just continue with the current speed and then brake, we will be very ready about that braking in future. Now, these are the benefits I mentioned, and the issues with this approach, or like some of the disadvantages, is that it's very slow to run, especially when we have nonlinear models. It's harder to debug because optimization is kind of a black box. We don't know what's going on, and it's hard to tune the cost factors. We don't know what's the relative importance there. And also the horizon is most of the time in places that the trajectory suddenly changes from one plan to the other due to, for example, reacting to a cutting scenario or a false positive. The plan completely changes. So this readiness towards future is not really useful in those situations. And obviously, we need a good vehicle model to be able to use that in the optimization. Now, a more practical approach is feed-forward, feedback. So in this case, we are relying, as a feed-forward, relying on the planner to generate a sequence of controls that are kind of based on some assumed vehicle dynamics. And then for the feedback part, we can just use a single PID, and this feedback part is kind of based on the current tracking errors. So this will be a very simple pipeline, and it's fast. It's deterministic runtime, and the method has proven to be really working in the industry as well. So, but the issues is that, of course, it doesn't have any lookat, so sometimes it could be very reactive, and the feedback only works in when the region is linear, and for non-linear vehicle dynamics it's a bit challenging to be tuned. Lastly, the controller outputs acceleration and steering command, and we still need to convert these into actuation input. So and there are the actuations we should be doing some tests, some experiments to get the response function. For example, the response of a brake pressure to kind of the deceleration of the truck. So these functions can be used by just fitting like a linear model or more complex model, but they are very important to be kind of characterized for each vehicle that we are using. So it's basically braking, engine torque to acceleration, or also on the steering side, like there are some parameters that we should estimate. For example, what's the steering bias and scale, which basically tells you how the steering wheel correspond to the front wheel. And you can go more complex. For example, that could be dependent on the speed of the vehicle. Okay, so that brings us to the end of this session, and we talked about a few of the things in control as well. So thanks for listening. Any questions? Okay.
Why not using the policy example
to directly output the control policy?
So I think like the planning slide shows that the output plan is just three to that. Is it possible to replace the one with the action?
Yeah, I mean that's possible, and that's, I mean, traditionally that's what has been used, right? But the planning gives you a more kind of more information, right? It's not just telling you like immediately what to do, but it's also telling you, okay, what it's thinking about future and why we are doing this immediate action, right? It gives you more information. So I think it helps the interpretability, and also like for the user to understand what is going on.